what I'm going to talk about is the quantum advantage in cybersecurity. So quantum advantage are two words that we've heard a lot about over in the last year. There's a lot of skepticism about what it means, when are we going to get it. What I'm here to tell you is that we already have a quantum advantage in cybersecurity. And I'm going to tell you a little bit more about what that looks like and how that's going to progress. Now, we have a problem. And that problem is that everything is unbelievably interconnected. Now, as I talk right now, I have a phone in my pocket. Everybody else does. And as we've established, everybody has been checking it. And checking it to do everything from talking to friends to opening your bank account. And all of these different interactions need to be secured. And so, how do we secure this? So the way we do it, and the way we do cybersecurity, is multi-layered. Now, almost everybody in this room, and almost everyone, has heard of encryption as a concept, right? You open your WhatsApp, it's end-to-end encrypted. What that means, we don't know, but we know it's good. Now, encryption is just one aspect of it. It's really the top-level layer. It's the software that's running things. But to do encryption, encryption is basically making a good lock. And to make a good lock, you have to have a good key. And so one of the things that back encryption is a key exchange mechanism. Now, Reed talked to us about the invention of public key encryption. And it's a way of sending keys securely so that you can open your lock without worrying about it too much. Now, the problem is making those keys is also quite hard. Now, ideally, you want your key to be fully random because you don't want anyone to be able to guess it. You know, if somebody could steal your key, that's one thing. If they can guess it, that's a bigger problem. This is why, for example, now when you make a new password, websites almost want you to write in Greek letters. They just want your password to be more and more random. And it's the same thing for the small passwords that your phone makes billions of times a second when it tries to send an encrypted message. All of them need to be random. Now, there is a quantum aspect to all three of those layers. So let's start from the top. I'm guessing most people have heard of post-quantum encryption. Hands up if you have. Now, post-quantum encryption is not quantum. That sounds weird. So post-quantum encryption is just there to protect you against quantum. What it means basically is that we've just found out that this amazing technology that we're building, quantum computing, is probably going to break all of encryption as we know it. So people got worried, and they said, you know what, we need to fix this. We need to have a way to actually have encryption that is what's called quantum secure. So a post-quantum encryption algorithm is just an encryption algorithm. It's a piece of very, very neat software that has been developed and has been designed to be resilient against the computing power of a quantum computer. And in fact, we've had post-quantum encryption algorithms before we've had quantum algorithms. So if you've ever heard of a one-time pad is a method of encryption that is information theoretically secure. There's no way to break it. Unfortunately, it's almost impossible to implement in an easy way, so we have to figure something else out. Now, let's go a level deeper. Key exchange. Here is where quantum starts to shine. So exchanging keys is a very hazardous process. Because ideally, you want to send it on a channel that you don't necessarily trust. You want to be able to send it without having to have like two little pots and a string between you and the other person. You want to send it on just a public channel, and people can use it as much as they want. Now, this is where quantum key distribution comes in. So quantum key distribution uses some of the weird properties of quantum mechanics, things like when you measure a quantum state, it collapses, which means that it loses some of the properties that it originally had, which means that you kind of know when somebody has measured a state. So that means you know if something you're sending your information on is compromised. And that's a big benefit. Because otherwise, you could send a key, and you might think it's perfectly secure, but it's not. So this is what quantum key distribution is trying to do. It's not an encryption algorithm in itself. It's just a way of sending keys in a very secure way. You still need a good encryption algorithm. So that's why a lot of people are thinking of combining quantum key distribution with post-quantum encryption systems in order to create something that's even more secure, something that's elegantly called the cheese hole model. Now, the next, nope, that's not the next. Yeah, that's the, so the last aspect is, of course, the randomness. Now, you might think this is the simplest one, right? Just make a random number. That's actually not true. It's quite hard to make computers act randomly. We've been designing them for a century now to act as predictably as possible. So to make a computer act randomly is quite difficult. It's not just that. The problem is you have three ways of generating randomness. You have just using a computer, just having a laptop, having an algorithm on it that kind of fakes randomness. That's not too good, because basically the algorithm itself is deterministic. It's trying to approach randomness, but it's not really going to get there. The next aspect is to use some kind of actual hardware implementation. So, some noisy hardware, and that noisy hardware, you try to get some randomness out of it. And that's actually quite easy because we make noisy hardware all the time. The problem with it is that it's kind of unpredictable. And you might think, maybe that's the point. I want it to be unpredictable, but not really. So it's not that you want it to be just unpredictable. What you need for a good random number generator is you need something that's predictably unpredictable. You need to know how many keys of randomness you can be able to generate with your system. So that might sound a bit weird, but let's run this small thought experiment. So you have a coin flip and a die throw. Now, which one is more random? So who thinks the coin flip is more random? Hands up. Okay. Who thinks the die throw is more random? And who thinks they're equally random? Okay. So I'm gonna do an icebreaker here. It is the die throw. But there is a good reason for that. Now, the reason why it's a die throw is because it's much harder to predict what it's going to land on than the coin flip. So if I predict the coin flip randomly, I'm going to be 50% right. That's my chances. With a die throw, it's only 1 in 6. Now, this simple example shows you that a random thing isn't just random or not. It can be more or less random, and that's what algorithms mean when they say, I want 128 bits of randomness. They don't say just I want 128 bits. It has to be 128 bits of randomness, and that's actually quite hard. How do we measure the randomness of any particular item? Now, you might want to run some stats, but you can't run stats on one thing. So just one number, if I tell you 10, that could be 10 of 100 or 10 of 1,000,000, you don't know. So the problem here is that we need a way to not only generate randomness, but to generate randomness in a way that's completely quantifiable. Now, the way we've done this is, instead of relying on noisy processes, which are unpredictable, we relied on a quantum process. Now, one of the interesting things about quantum processes is that fundamentally, you can never know how they're going to behave. And that's how the initial controversy started. Right? You pick the simplest quantum system you can pick, the equivalent of a quantum coin toss. And no matter how much information you know about the system, no matter how much control you have over it, it will act completely unpredictably. But what's nice about it is that it acts in a predictably unpredictable way. Give me a quantum system, and I can create a model for it, and that model is not only going to tell me that, you don't know anything. It's going to tell me how much exactly I don't know, which is good for your self-esteem. Now, the idea then is, how do we take this incredible system and implement it in a real-world scenario? Now, the reality is it's quite hard. You can't create just a quantum system. There's no such thing. Everything that we make has a little bit of quantum in it and a little bit of regular stuff. That's just how it is. So how do you separate the two? And that's been one of the roadblocks to using quantum random number generators, to using quantum processes, because how do you actually prove that the noise, that the randomness that I'm extracting at the end is coming from the quantum process itself and not from just a bad detector that you have in the middle? How can you tell the difference? And so what we did is develop what we call the source device independent self-certification protocol. Yes, it is a very long sentence. And so for now on, I'm going to just call it the DISC protocol. Now, the DISC protocol, basically what it does, in a nutshell, is it leverages another nice property of quantum systems, which is correlations, that allows us to say exactly how much quantum randomness can be generated at any given time. And so that you know, when you have your final signal, you only have that amount of entropy. Now, that might sound a little bit weird, right? Because you might think that if I get at the end 2 bits, that it has 2 bits of entropy, but that's not true. 2 bits can have much less than 2 bits of entropy. In fact, 2 bits can have 0 bits of entropy. What this protocol allows us to do is exactly quantify that amount. And not in a statistical manner. This isn't some kind of statistical test. And funny anecdote, one of the ways we test if a random number generator is good, one of the standard ways, is through one of something called the Statistical Test Suite that was developed by the National Institute for Standards and Testing in the US. This is world-renowned organization, world-renowned test. You download the test, run it, it tells you if the random number generator you're using is random or not. You go to the first page of the documentation of the test, and that page tells you you cannot use statistical testing to make sure that the system is secure. So, you know, maybe we have more things to worry about. But in reality, we bypass all that. We don't use statistical testing. What we use is directly the actual architecture aspect of it. The quantum system allows us to do that. And now, when I said the quantum advantage is here, and I'm not saying that as, you know, we've developed the technology in the lab, we're now going to go out and build it. I'm saying that by meaning we've already built it and we've already deployed it. So right now, our system is being used to secure and to enable trusted encryption on an active project to secure communications in the UK. And this is the first step for us. The technology that we're talking about is no longer future tech. This is a full product. If you want to buy one, just get in touch with me or George, he's somewhere out there. But it is a product that is ready to go out there. And it is a product that isn't hypothetical, whose advantage isn't theoretical. The advantage is quantifiable. And what we're aiming to do is get our product from its current stage, which is still a bit bulky. It's about, well, the smallest version is the size of a PCIe card, is to get it to a completely integrated chip. Now, that's going to take time. It's going to take a lot of effort. But by doing that, it allows us to really take the next leap forward and provide this kind of quantum-enabled, trusted encryption, not just for high-end applications, not just for communications, but also for your TikTok machine. Now, this is going to be the end of my talk, and I'll be happy to answer any questions that you may have. And thank you so much for having me again.